Welcome, future geospatial professionals. Let's jump right into this explainer. We're going to map out the history of geographic information systems today, but honestly, this isn't just about memorizing some dates from a textbook. We're going to look at this history as the development of an evolutionary toolkit, the exact toolkit you'll be relying on every single day to build your careers. You're stepping into a field with an incredibly rich, dynamic past, and understanding how these tools were forged is absolutely going to make you a sharper, more capable spatial analyst. Here is our agenda for today. We'll hit the core concepts of GIS, meet the father of GIS, go from command line to GUI, check out the modern software ecosystem, explore the open source frontier, and finally, look at adapting for future security. Let's get to it.
Section 1. Core Concepts of GIS.
Okay, before we dig into the history, let's just make sure we're on the exact same page about what this technology actually does. At its heart, a geographic information system is a dynamic, computerized environment used to capture, store, analyze, and visualize spatial data. But, it is way more than just a digital map. By tying spatial data directly to attribute data, basically connecting the where to the what, GIS lets us ask really complex questions about the world, revealing hidden relationships and patterns that traditional paper maps just couldn't handle.
I like to think of GIS as taking the messy, three-dimensional physical world and flattening it out into a neat stack of transparent digital sheets. You have your vector building blocks, right? Points for wells, lines for roads, and polygons for property boundaries. And you can layer those right alongside continuous raster grids, like satellite imagery. By stacking these transparent layers, we can analyze how totally different geographic features interact within the exact same physical space.
Moving on to Section 2, the father of GIS.
So, where did this brilliant concept actually originate? Well, our professional family tree traces back to the early 1960s, which was a time when manual mapping was literally hitting its breaking point. Enter Roger Tomlinson, a visionary English-Canadian geographer. Back then, he had this absolute chance encounter on a flight with Lee Pratt, who was heading up the Canada Land Inventory. They got talking, and that single conversation quite literally changed our entire field forever.
See, Pratt had what sounded like an impossible mandate. He had to map Canada's massive rural land capabilities for forestry, agriculture, and wildlife across the entire nation. Tomlinson immediately realized that trying to do this with manual paper map overlays would be painfully slow, highly inaccurate, and just ridiculously cost-prohibitive. So he took a huge swing. He boldly proposed partnering with computer scientists at IBM to completely automate the spatial processing and overlay process.
And the result of that partnership was astounding. In 1963, Tomlinson directed the development of the Canada Geographic Information System, or CGIS. This was the world's very first true computerized GIS. It brilliantly introduced true digital vector topology, which basically means encoding lines as arcs so the computer actually understands spatial relationships. It completely revolutionized data management by separating locational geometry files from the attribute tables, and even utilized custom drum scanners to automate digitizing paper maps. That's exactly why Tomlinson is universally recognized as the father of GIS. Meanwhile, at the exact same time south of the border, academic centers like the Harvard Laboratory for Computer Graphics were making their own massive waves. Led by folks like Howard Fisher, the lad pioneered early cartographic software. By mapping the Delmarva region, they proved that mainframe computers and basic line printers could actually effectively process overlapping spatial grids. That totally set the stage for advanced spatial surface analysis down the line.
All right, Section 3, Command Line to GUI. Let's look at how all this history builds into the tools sitting on your lab desktop right now. This timeline tracks your commercial toolkit's evolution. We go from the totally command line-based arc/info in 1982 up to the revolutionary graphical user interface of ArcGIS Desktop 8.0 in 1999, all the way to the launch of the modern 64-bit powerhouse that is ArcGIS Pro in 2015.
Back in the 1980s, Esri, which was actually founded by Jack Dangermond, an alum of that Harvard lab, released arc/info. Now, looking at this 1985 abstract, it might look like it belongs in a museum, but led by developer Scott Morehouse, it revolutionized the industry. It implemented a true georelational model, meaning it combined a strict topological model for mapping locations with a standard relational database model to handle all the attributes. This brought crazy efficiency to geoprocessing, finally letting analysts do complex polygon overlays right inside the data model.
But here's the catch. Arc/info required typing raw text commands on specialized workstation computers. So the real game changer happened right around the turn of the millennium. The release of ArcGIS Desktop 8, specifically ArcMap, gave us an intuitive graphical user interface. Instead of coding, you could finally visually edit layers, apply symbology, and design maps. That massive leap dragged GIS out of isolated, highly technical computer labs and dropped it right into everyday professional offices.
Next up, Section 4, the modern software ecosystem.
Fast forward to today, and let's talk about the immense analytical power sitting at your fingertips. Platforms like ArcGIS Pro represent a huge leap forward. You now have access to tools like 3D voxel layers that let you visualize really complex atmospheric or oceanic data over space and time. You can use trace networks to map out connectivity logistics across massive railroad systems. You can use link analysis to discover hidden relationship patterns between moving objects, and you can even run interactive suitability modeling to instantly find the absolute optimal locations for new projects based on competing criteria. It's wild!
And the glue holding this entire proprietary ecosystem together is the geodatabase. Unlike older clunky formats that could only hold one type of geometry per file, a geodatabase is a highly sophisticated digital container. It stores multiple feature classes, ties spatial features to attributes, and enforces really strict behavioral rules. It literally dictates exactly how a road intersection, a utility pipe, or a property line is allowed to interact with the things around it.
Section 5, the open source frontier.
Now, as future professionals, I need you to know that the proprietary software you use in class, that is really only half of the modern landscape. While those proprietary ecosystems offer incredibly robust desktop tools, open source platforms provide specialized, highly customizable power, especially for the web. Engines like MapServer offer absolute blinding speed for publishing interactive mapping applications and spatial data right to internet browsers. Originally developed in the 90s by the University of Minnesota and NASA, MapServer is built on the C programming language to maximize rendering speed. Open-sourced in 1999, it accesses hundreds of formats through the GDOL translation library. What's fantastic is that it perfectly complements your commercial desktop software by deeply supporting OGC standards. These are basically universal rules that guarantee the spatial data you create can be seamlessly and openly shared across the web, regardless of what software the end user happens to be running.
And finally, Section 6, adapting for future security.
Let's talk about your future for a second. Your career longevity won't just depend on making great maps. It's going to depend heavily on how well you manage your organization's data infrastructure and security. Right now, leaving organizational data in older, sunsetted software like ArcGIS Desktop 10.8 exposes companies to massive risks. Legacy software is completely bottlenecked by 32-bit memory limits and single-threaded constraints, meaning it just chokes on large modern datasets. And even worse, it relies on deprecated components like Python 2.7, creating severe, unpatchable cybersecurity vulnerabilities.
So, here is your professional imperative. As a new geospatial data scientist entering the workforce, championing the migration from outdated legacy systems over to secure 64-bit multi-threaded environments, that's just as important as the actual spatial analysis you perform. You are the vanguard, making sure decades of geographic data remain accessible, efficient, and above all, secure.
We've mapped the whole journey today, from slow, manual paper overlays to Roger Tomlinson's visionary CGIS, all the way up to cloud-connected 3D modern platforms. You are inheriting a truly incredible evolutionary toolkit. So the question I'll leave you with today is this. Armed with the history and the sheer capabilities of these tools, what real-world geographic problem will you be the very first to solve? Thanks for hanging out with me on this explainer, and I can't wait to see what you build.